in 2012. And he has done his PhD in NIT Tishnapalli in 2017 in the Department of Electronics and Communication Engineering under the guidance of Dr. P. Muthu Chidambaranathan. And after his PhD, he worked in Sankhya Labs Private Limited, a software-defined radio-based company, as a senior member, a technical assistant for a year. And currently, his areas of research include 5G and beyond wireless communication, physical layer aspects, signal processing, massive MIMO, ultra low latency communication, and noma. And he has published his research papers in many of the reputed SCI index journals. And he was one of the co-principal investigator of a project titled Receiver Design for the Low Latency 5G Wireless Communication, and it was funded by Sri Lankan Technological University in collaboration with Professor Dr. Nalin from Russia, who is a fellow of IIT UK. Over to you, sir. Now,
Thank you, ma'am.
please. Thank you.
Okay. Thank you, and thank you for the opportunity, first of all. And so today, our topic is candidate technologies for 5G and beyond wireless communication. People who are working on this already in wireless might have familiar with some of the terms I'm going to say, but definitely for others, it will have some kind of you can have definitely have some kind of ideas in case if you are about to start the research. Okay, you can just go ahead with whichever topic is interesting here. So this is a physical layer perspective, and right now people are even in the recent call for I have seen the project call for I have seen 6G and 7G. Maybe I have to update my titles because of 5G becoming too old for research. Even it is not completely implemented, but for research 5G is getting a little older. Okay, so that much amount of phase it is going on. Okay, so today this is our topic of discussion. Generally, for any communication system, this would be the motivation. So here we are considering a mobile communication scenario. Okay, so here the main motivation is to increase the network throughput. So what is the network throughput? Network throughput is how much data rate is served within a square kilometer. It means within a square kilometer in the sense it could be a hexagonal cell. Okay, like microcell, macrocell, umbrella approach. Okay, so within a hexagonal cell, that means within a square kilometer, effectively, how much bits per second are we going to serve? Okay, so that would be the throughput and how these factors can be increased. You could see there are three different parameters that actually contribute to this throughput. One is cell density, another one is available spectrum, and another one is spectral efficiency. Okay, so tampering on any one parameter, that would definitely have a better throughput. Okay, so firstly, what is cell density? Cell density is cell per kilometer square. So in case if you are improving the number of stations, increasing the number of stations, like as I said, umbrella cell approach, like microcells, macrocell, nowadays femtocells are also there. Okay, so in case of dense area like Hyderabad or Chennai, I mean densely populated people, densely populated there, right? So those kind of areas go for this, definitely have to go for this microcell approach. And on increasing that, the cell density, cell density part can be easily increased. Okay, but the problem is practically there are a lot of cost is involved in that. A lot of cost and something socially has to be dealt with because people don't want any mobile towers over their home or near to that, even near to that, because there are, of course, there are some problems. Okay, but anyway, there are some practical difficulties. I mean, even more practical difficulties to tamper that parameter and to get a better throughput. Okay, so we can't keep increasing the base stations. Okay? So, but small base stations will be there for 5G. So that can be done. That can be where people can be easily convinced there. And cell density is one part, and the next one is available spectrum. So generally in sub 6 gigahertz band, the available spectrum is sparse in nature, actually. So this available spectrum, if you see, the cost involved in purchasing this available spectrum is huge. Like recently, I have gone through a news like this. Troy has fixed the price, and around some 2,400 megahertz were auctioned for 5G. Okay, so who are all the players, or who are all the network providers, or who bought this spectrum? Or one is Bharti Airtel, another one is Jio, of course, and one more player is also there. That is Vodafone Idea, VA. So these three fellows are competing, and in on par with Jio means it is Bharti Airtel only. Some around 5% of the purchase is actually holded by this Vodafone Idea. Most of the spectrum is majorly purchased by Jio and Bharti Airtel. Okay, Jio, yeah, of course, it is very much leading there. And Troy is someone who fixed the price. They are the regulatory body, Telecom Regulatory Authority of India, and they have fixed a reserve price of around 4 lakh crores for this 2400 megahertz. Okay, and also it's not about the 1 megahertz at lower frequency is not the same price at the higher order frequencies, because at lower order frequencies, um, the the price is so much, like say 700, around 700 megahertz, the actually the auction has failed around 700 megahertz, because the spectrum near 700 megahertz they couldn't able to sell because of its base price, because base price is more than like 6,000 crores for 1 megahertz. For 1 megahertz, you they have to spend 6,000 crores to purchase 1 megahertz. Whereas when we go to some 3.3 to 3.6 gigahertz, they are purchasing at 500 crores per megahertz. Okay, so these price varies with respect to the frequency ranges as well. However, as millimeter wave progresses, millimeter wave thing progresses, uh, the uh, the spectrum availability. I mean, the spectrum availability also increase, which means that the base price will also be very less. Okay, so that they can be easily auctioned. But the problem is they can't handle it very easily. Okay, so a lot of signal processing and a lot of base stations has to be deployed to make it practically possible. So this is about the available spectrum. I hope the point I am trying to suggest is the available spectrum. If I am trying to increase the available spectrum and we are trying to increase the throughput, means then there is a problem. Like cost is a problem. Okay, now the last one, spectral efficiency. Okay, so this deals with the technologies we are going to use. Okay, so the spectral efficiency, for increasing the spectral efficiency only, that means how efficiently we are using a spectrum. You could see the unit of that is bits per second per hertz. That means within 1 hertz, how much bits per second can be delivered. That means how much data rate could be delivered. Okay, so that is spectral efficiency, and through some new technologies that is coming up, our discussion is mostly concentrated towards how efficiently we are going to make use of that spectral efficiency parameter. Okay, how we are going to contribute to that spectral efficiency parameter, and this is bits per second per hertz per cell, because per cell is indicates that we are dealing with only one cell right now. Okay, so this is the overall motivation of the communication, the mobile communication particularly, and this is a basic evolution everyone might have known, starting from 2G. I think I heard that most of the people attending are faculties. I'm sure faculties right now would have experienced all these technologies like GSM, CDMA, GPRS Edge, and WCDMA. Definitely CDMA, HSDPA, HSUPA. Even we are now experiencing now with BSNL, H plus, like that. HSDPA is being used. That is high speed downlink packet access, HSDPA, high speed uplink packet access. Okay, so that provides us a data rate of 5 to 30 Mbps. So 5 to 30 Mbps means it is not for a single person. 5 to 30 Mbps means it is for a base station. It is per site. Let's say per site. Okay, per site it can provide till 30 Mbps. That means this 30 Mbps will be shared among the users within them. Okay, so if we have a dedicated receiver for us, so there if we are using HSDP or UPA, definitely we can have this 30 Mbps. Okay, then one more thing is EVDO card, evolution data optimized. Mostly it comes under this broadband internet access. We actually go for this USB dongles and routers. So those things comes under this EVDO technology. Okay, so this 4G, of course, we are right now we are experiencing definitely LTE and WiMAX. Um, the the other technologies, say this is the summary of this table actually gives a summary of what is the evolution and what is the basic services there that we are providing. Okay, so what kind of improvisation has been done to recollect from your memory. You could see that in 2G or 2.5G means GPRS, when edge technology is introduced, that is 2.5G. Even now edge is there with when we are using BSNL. Sometimes this edge will also be shown. I'm not sure about Airtel, but this 10 to 100 kbps. So overall, the data rate it could obtain is 10 to 100 kbps, and voice and data are possible at that time. Okay, only voice and few data. Yeah, and later on in 3G and 3.5G, that is this HSDP and UPA thing. I'm sure you would have seen some ads from BSNL that you can do a video call throughout India. Okay, so you could see that is one ad at that time. It was very famous. You can directly go for a video call. Later on comes the 4G, and I don't have to explain much on that. So this is the evolution of this mobile wireless communication. Okay, so uh, now let's get into this 5G. Okay, so what are all the targets of 5G? I'll give a brief on what could be what are all the aims and what their objective is. So firstly, they are trying to give a data rate of 10 Gbps for uplink and 20 Gbps for downlink. So as I said earlier, in real time we won't experience this 20 Gbps at the downlink, because that is for dedicated cell. Okay, that is for dedicated cell. So in real world, we would be almost experiencing some 50 to 100 Mbps. Okay, so that is one thing, and better spectral efficiency. And with this efficiency spelling is wrong. Better spectral efficiency, and this if we, the spectral efficiency can be improved, as I said, the technologies we are about to discuss, that is actually going to increase this spectral that actually going to increase spectral efficiency. So that's why this session is for complete session is for. And device connectivity, they are the 5G is targeting around 1 million users per square kilometer. 1 million users in the sense there could be a lot of devices. Like, it's not specifically users, but it is more of a devices. 1 million devices per square kilometer. Why it happens is that we know few things about IoT. So IoT cannot be active without communication. Okay? Without communication, IoT is null. So how they are going to communicate with each other? How they are connected? So even we are there. We have a smartwatch with us, and there is something called Google glasses and all there for navigation purpose, and heart rate monitor can be fixed, or Bluetooth headset. So everything, if you are making it to connect to some internet, so there you could see how many devices. So anyway, this is a future technology. So definitely more number of users will get connected, and more. So they are targeting to make things very smart. So this is a role of 5G. So this is an enabler of IoT or Internet of Everything. Okay. So and another target is it has to support mobility and coverage. Actually 4G supports this mobility better, like 0 to some 0 miles per hour to some 310 miles per hour itself it can actually support. That means if you are traveling in some bullet train or something, definitely 4G can provide that mobility. But with 5G, the problem is it it has the problem of this using the millimeter wave. If you are going for the millimeter wave, when we are moving up until unless we are operating at less than in the sub 6 gigahertz, we don't have a problem. We don't have much problem. But when we are going for millimeter wave communication, then definitely this coverage will be a huge problem because right now right now the coverage is I mean for 5G it is now been operated in 4G band, uh, and still this coverage is not completely tested, but however theoretically speaking this coverage region will be very much a problem when we are moving on to the millimeter wave frequency because it cannot penetrate that easily. So it cannot penetrate easily, and it don't have much multipaths to deal with. So such LOS is required. So if a multipath is there means then LOS is not a major concern, but LOS, that means the line of sight, is a major concern with the millimeter wave. So there are technologies for that too, and this is a area where we are working at a URLLC, ultra reliable low latency communication. So ideally, it is expecting some, ideally in the sense some emergency situation, it is expecting some 1 millisecond of latency, and in other normal circumstances, we will be having some 4 milliseconds of round trip delay or latency. Okay, so the thing is, why we need this low latency? So just imagine that driverless cars are also coming up. So driverless cars, what does that driverless cars mean? So let's say we have a driver module installed in our home, and we have a car standing outside, and we want to drop our guest in some railway station or somewhere, or in an airport or somewhere with our car, and suddenly you are using the driver module installed in your home, and the car is going without any driver, so without any driver with only your guest. So suddenly in between some kind of obstacle is coming means then a brake has to be hit. So in case if the brake is applied at 1 second, and that second and that few after some 30 or 40 milliseconds, okay, even it can take more, like say it is more than 100 milliseconds. Okay, if it is taking 100 more than 100 milliseconds, then it would be, by time it would be too late to react. Okay, so there is a possible of collision with that obstacle. So to avoid that we require latency. Even telemedicine, telesurgery, so those things are also heavily depending on this latency part, and there are few codings available for this ultra reliable low latency communication, and yes, and we are working on that. Fine. So another one is less energy consumption. So this energy consumption, when we talk about the mobile communication, there is a lower energy state. Like say when the mobile is, when you don't receive a call, when you are not receiving call, when the mobile is in some idle state, or when it is not used, just imagine that it cannot keep a big, anyway it is been intact with your base station, but the problem is with minimum amount of energy, it has to be in connection with stay in connection with the base stations. And also once a call comes in, so it has to be more energy efficient. That means energy efficient in the sense with the less amount of energy it could able to decode someone's voice or even data. Okay, whenever you are not using the phone, it has to be stay connected to the base station. That is the low energy state. So from switching from higher to lower energy state, it is, yeah, they are trying to have it less than 10 milliseconds. Okay, so suddenly it has to go to the low energy state. So that you can save more batteries, and this battery life can be used for some gaming, high graphics gaming purposes or something. So this is one contribution that was aimed by this 5G. And apart from that, they are expecting, when we go for nodes, wireless nodes, they have to wirelessly power this nodes. So there is a topic based on that too. That is simultaneous wireless information and power transfer, that will be covered in my session. And the battery life has to be more, because there are some parts where the nodes cannot be accessed easily. Let's say yeah, we are putting the sensors in the factories or industries, and at times, due to the temperature or non accessibility of that sensors or nodes, it is very difficult to power it up and take the data from them. But when we are powering it wirelessly, then definitely we can take what is the temperature data or what is the pressure inside that boiler, or any kind of data can be accessed there. Even in forest region, these nodes can be used. Not every time you want to take that particular sensor and you want to see the reading, but definitely with less energy power consumption, you don't want to replace this node every time. Okay, so these are all the targets of 5G, and I think I have almost covered what the 5G is aiming at, and what is the support, what could be the frequency band and its coverage when it comes to the 5G. So basically, 5G operates at three different bands right now. One is, yeah, as it is given here, it is operating even at less than 1 gigahertz. Okay, so the problem is, in less than 1 gigahertz, so we don't have more data rate. Okay, so the peak data rate is not more than 100 mbps. But when we are moving on to the higher order frequencies, the data rate gets better, but the problem is coverage. When we here you could see here you could see this is the coverage of the millimeter wave. Here the data rate is 10 gbps, but the problem is the coverage is very small. Okay, so because of this, the coverage, uh, the uh, the millimeter wave is very complicated to deploy, but definitely it is in pipeline of 5G or 6G development. Okay, so this is due to the propagation loss. This is due to the propagation loss at higher frequency. So they are going for this massive MIMO and beamforming kind of techniques and all. So this is about the coverage comparison. You could see as the frequency increases from bottom to top, as the frequency increases, you could see there is a steep increase in the data rate. However, the coverage is becoming lesser and lesser. Right now, 5G, even in US or Canada, right now it is being piggybacked by this LTE. That means some of the technologies in 5G are being used in the bands of LTE. So right now the coverage is not completely it is not completely computed. Okay, so they have to fully deploy anywhere it is, and they have to make the coverage comparison. So right now this comparison is based on only the frequency range. Okay. So as I said, to add a few things to this, there was 800 megahertz that is being purchased by Geo and Airtel. So around 800 megahertz to increase the capacity of 5G. To increase the capacity of 5G, they have purchased it, and even 3.3 gigahertz to 3.6 gigahertz, Geo has purchased. Like overall, they have purchased around 1,700 megahertz Geo, and Airtel have purchased around 350 megahertz. So anyway, this Vodafone Idea, they have purchased very less only. Okay, but in some areas, definitely they are very effective. Okay, so these are all the technologies we are going to discuss today. One is noma. This is a very famous term. Even I have seen some topics related to noma just before my session, but I'll give some kind of mathematics behind this. Uh, okay, and non-orthogonal multiple access, millimeter wave MIMO, massive MIMO, full duplex radio technology. Full duplex radio technology is one technology that that feels very good while studying. So another one is simultaneous wireless information and power transfer. So the first one is NOMA, non-orthogonal multiplexers. There would have been a lot of things about NOMA in your previous session itself, I guess. And just to deal it in a theoretical way, I'm just going ahead. Like orthogonal multiple access schemes or like TDMA, CDMA, or OFDMA are there. Now what the orthogonal multiple access do is they have a separate resource block for each and every user. So but in the same time or in the same frequency, not more than one user or not more than one user will be transmitting in the case of OMA, that is orthogonal multiple access. Now getting into NOMA, non-orthogonal multiple access, within the same frequency and same time, they more than one user is going to transmit the data. So how it is possible is they are separating the users in power domain. Okay, so this is one of the key radio access technology in 5G network, and in the power domain, the users are actually divided, and based on the power levels, the user data can be differentiated, and it also enables high spectral efficiency because that will be proved in an analytical way. And the receiver side, they will be using the successive interference cancellation. So it's a kind of signal processing, but still that will definitely consume there will be some increase in the computational complexity in the receivers. Okay, so this is a basic NOMA diagram, very famous diagram. Any NOMA paper, if you open, mostly this diagram will be there. Okay, so what they do is there is a far user, there is a near user. So the base station is going to serve them in the same frequency, and at the same time they are going to serve them. So how it is possible is in the power level they are going to be differentiated. Okay, so why a near user and a far user? Why not two near users? Why not two far users? Why not medium users? Like that, a lot of questions will be there. The thing is, that's what enables this NOMA. That's some basic core of NOMA. The near user will have a strong connection with the base station, whereas the far user will have some weak connection with the base station. So how they are going to serve these two users? So firstly, we take the data. Firstly, this S1 is user 1's data and S2 is users 2 data. So these both the data are available in the base station. Now I want to give the data S1. The base station has to give the data S1 to one guy, the nearer user. I think S1 user 1 is far user. This is far user data, and S2 is the near user data. Far user data and near user data. Since we are going to transmit only once, we want to combine them very smartly. Like there is P1 and P2, that is a power factor. Okay, so overall, if you see, this is P1 plus P2 must be equal to 1. That is 100%. P1, it can be any number of percentage. So P1 and P2 should constitute 100% of power. Okay, whatever the transmit power is, and rho s is the SNR levels, and we could see P1 and P2. For near user data, what they do is they give only less power, because a near user, if someone is standing near us, that means the base station, uh, even if it sends at very low power, it could be able to decode its own data because it has a very strong connection, right? So whereas if you are going for a long user, they have to use more number of hours. So based on that logic, this P1 will be very much greater than P2. Okay, so this power levels are compared based on the distances, and we have this transmit power, total transmit power as PS, and that is a factor of, that is one of the factor of this total transmit power is a factor of this rho s. Rho s is nothing but the SNR. SNR. Okay. So now this is superimposed. That means user 1 data and user 2 data both are superimposed, and a single data is being framed. Now this data will be transmitted, they will be broadcasted to user 1 and 2. Now they will be receiving it. This S will be the superimposed data. S will be received by both the user 1 and user 2. Now S will be received by the ith user. So ith user in the sense it can be either user 1, that is the far user, or it could be either the near user. Okay, if I equal to 2. So we have yi is equal to hi into s plus ni. Hi is the channel coefficients and ni is the additive white Gaussian noise, or generally a noise. Okay, so we have received the signal. Both the users have received the signal. Now the challenging part is how they are going to separate their, how they are going to take their own signal to them. Okay, so now at for user, what happens is its component is that is the S1 component actually has a better power, right? So P1 has more power when compared to P2. Okay, P1 is higher when compared to P2. So that means this part, this is a far user part, and he will receive that part very strongly, and this part is a little weaker. Okay, so this part, in the superimposed part, this part is a little weaker. So directly he can go for the decoding. Directly the far user can go for the decoding, provided he will have some signal to, not SNR, but it is signal to interference plus noise ratio. Why? Because there will be some part of the near user signal as well. So what this far user does is it considers that near user signal as a interference. Okay, so analytically speaking, the SNR will be SINR, that is signal to interference plus noise ratio. So this part here is interference. Okay, this part here is interference. Why? Because this signal here is the interference for the far user. Okay, for the far user, and so we are computing the interference power and we are putting it here. Okay, so that's why we square it whatever it is given here, and we will have it as a power in the SINR equation, and we have h1 square. So the h1 square is h1 is the channel coefficient that gets multiplied when we receive at the receiver. Okay, now with this, using the Shannon's capacity theorem, we could say that it is the capacity is bandwidth times log 2 of 1 plus SNR or SNR. So I'm just assuming that the bandwidth is unit bandwidth. We are just considering a unit bandwidth. So log 2 of 1 plus, this is the SINR term. Okay, so this is the achievable rate for user. Okay, what about for the near user? What he will do? So near user will receive the far user component as a strongest component. So what he does is, first he will decode the far user part. Okay, so at that time he consider his own signal as a interference. Okay, so this is the far user signal power, and this is his own signal. He is considering it as a noise. Okay, so this term here is the interference right now, and the corresponding SINR is given given here. This why we are having this oneness. This indicates it's a normalized noise. This whole equation is actually normalized with the noise. Just a minute. So this user 2, so this user 2 first decodes the for user data, and after that he will subtract the for user data from the near user data. So y2 is something that has been received. Let me have this as y2 prime. Okay, that is better. So y2 prime is actually equal to y2 minus for user data, that is s2, provided he multiply that with some snr or something. Okay, so what happens is, if you are writing, let me say that, let me substitute this equation here. So what happens is this term will go. Okay, so this is what we call it as successive interference cancellation. Okay, successive interference cancellation. Why? Because we are staying, the user one is near, so the nearer user are real, have a real problem on dealing with noma, because they have to do this SIC and all, and this is not restricted to only one user. This can be extended for any number of users. So that means they have to keep doing the SIC. As we go closer and closer, that means as the user go closer and closer to the base station, the number of layers of SIC they have to execute is very large. Okay, so that is one problem with the noma. And to continue that, we have now we have cancelled this, and now right now in y2 prime only his own data is there. Okay, so what he does is, he can directly now go for this decoding, and right now he won't have SINR, rather he will be having SNR, the signal to noise ratio, because he has cancelled the interference. That's why we call it as a successive interference cancellation, right? So he cancelled that interference, so SINR is now converted to SNR. So that's why we have it like this here. In the denominator you will be having actually 1. Okay, that indicates the normalized noise. Okay, now the overall achievable rate for user 2 is log 2 of 1 plus SNR, because his own data, what is his own data? So for that, what is the achievable rate? Okay, so this is the achievable rate of user 2. Now what is a sum rate? Sum rate means it is the addition of both the individuals achievable rate. So this is user 1's achievable rate, and this is user 2 achievable rate, that is taken from here. Okay, now on doing some simplification, see, this simplification is purely for making a comparison with the OMA, and we could see that if we check on this H1, we can say that this one could be negligible. Okay, this one could be negligible. So when compared to this component, so we are just taking out this one first. Okay, we are ignoring this one first. So then when we just do the cancellation, then we have P1 by P2. So thereby we are changing this equation, this particular equation SINR as P1 by P2. Okay, now we are rewriting this equation here, and this equation can be rewritten in the form log to the base 2 of 1 by P2 plus this is based on log of A into, we are just combining it. Okay, so on combining this we will be getting this particular term here. Okay, so this is the achievable rate at higher SNR, achievable the sum rate of the noma system at the higher SNR. Now getting into OMA, we have half the bandwidth for let's say we have half the bandwidth for user 1 and half the bandwidth for user 2. So that's why we are putting a component half here. Okay, now user 1 data is separately sent in the half bandwidth, user 2 data is also sent in the separate bandwidth, I mean separate bandwidth and at the, or let's say separate time instant. Okay, so what happens now, this will be the sum rate for them. Okay, so that's why there is no interference, nothing is there. But still, why we are going for noma? Okay, so that justification will be given here. The thing is, at higher SNR, let's say this still the users are near user and far user only. We are considering the same scenario and we are going to apply the OMA. Now this near user, right, this near user fellow will be having the strongest of channels. So what happens is, this equation here, this H2 will be very large. Okay, this H2 will be very large when compared with H1. So this will be negligible, and I'm just making it to 0. That's why we are getting a sum rate like this. Okay, now what happens for noma? This is the sum rate of noma, and we could do a clear comparison that the first one is half, component half is there. Okay, so here we have unit bandwidth, here we have unit bandwidth. So the capacity there itself, it is very higher in terms of, for noma the capacity is very higher there. Okay, now getting into this log 2 of rho s h2, here also the same component is there, here also that component is there. But what about 1 by p2? What about 1 by p2? P2 is anyway, it is smaller than 1. So 1 by p2 will be very larger. I mean, not very large, it is greater than 1. So overall, if you see, Noma has a better sum rate. Better sum rate in the sense, better spectral efficiency. So better sum rate than the OMA. So this actually compares with OMA and NOMA. Yeah, so far I would like to uh, take up, I have taught something, I would like to take up some questions now, then I can move on to the next part. Yeah, OMA, right now we are using only OMA, sir. Whatever technology we are using, OFDM, that is actually OMA. Yeah, yeah. Like if you are having a unit bandwidth, half the bandwidth will be used for user 1 and half the bandwidth will be used for user 2. Yeah, okay. Thank you, and we will continue on the session. So this is OMA versus NOMA. So some might have very much familiar with this, or some might have familiar during this FTP. And we will move on to the next topic. This is RSMA, rate splitting multiple access. So if you just check, this RSMA is very similar to NOMA. RSMA, rate splitting multiplexes, is very similar to NOMA, but the um, the overall setup, like say, I said one disadvantage with NOMA, as we have more number of users, more layers of SIC they have to do. So instead, if I could do SIC only once, if more number of users are there and we could use only one time, if you are doing SIC means, then that is fine, fair enough. We have very less computational complexity, and with some better multiple access technique. So here in the rate splitting multiplexers, what they do is they take, uh, let's say a base station has to transmit two user data. Okay, so this part here, consider this part here as base station, and these fellows are users. These fellows are users, and this base station wants to transmit user 1 data to user 1 and user 2 data to user 2. As we discussed earlier, OMA uses half the bandwidth or half the time instant for one user, and for half the bandwidth for another user. Okay, now coming to noma, it uses the same bandwidth for both the user, but they are differentiated in the power levels. Now getting into this rsma, what it does is it compares the data, user one's data and user two data, and it picks up the common part between them, common message based on the user one data and user two data. It actually separates the common part apart, and common part in the sense, so that the receiver could decode the common part very easily. The common part will be given to both the users. Okay, both the users will do the sic, they will decode this common part, and they will do the sic, and they will get back their own message. Okay, so this is the idea behind this rate splitting multiple access. So that what happens is, in case if you are accommodating more than two users in the same bandwidth, in the same spectrum, if you are accommodating more number of users, then together, if say five users are there, for five users, some common part they will be deriving, that common part, and these things will be decided by this encoder actually. Okay, they combine this common part, because common means there is some part of, anyway it is ultimately it is zeros and ones, but when it comes to the receiver side, when the message is coming to me, or coming to any other person that is nearby, some zeros and ones may be similar, some zeros and ones may be similar to me and him, or it can be made similar using this encoder. Okay, so if I am receiving 01, that 01 is the common part means. So 01 means, yeah, in the encoder table, 01 means something for me, and 01 means something for him. Okay, so in that way, this encoding and the decoding will happen. So and the private part will be also combined with the common part, and they will do the decoding very easily. Okay, so this is about the rates. I'm not getting into the mathematics of this rate splitting multiple access, and because right now I don't have the perfect math for this. But here you could see roughly, you could see that there is a linear encoder here. There is a message combiner. That means the message, this W1 is user one message, and W2 is user two message. And this message splitter, what it does is, it will take out the common part from user one and user two, and they combine it as a single part, W12. Okay, that is a common part. So this message combiner will make sure we get only one common part out of this two messages, and there is a private part. There is a private parts here, private parts of the message. So that will be given to the encoder, and finally through the linear precoder, it will be transmitted through that. Okay, so here in the receiver, what it does is, firstly it will decode the common part. That's why we have decoded the common part. Then we go for this SIC. Then we go for this SIC. Why we have an encode and a precode is that, because whatever message it has been transmitted has undergone encoding and linear precoder. So before doing this SIC, they have to make sure they do the encoder and precoder thing. Okay, then channel coefficient also important. Okay, so this is about the rate splitting multiple access, and this overcomes the problem of multiple layers of SIC, and it also, the near user far user things are also not so much of a concern with the RSMA. In noma, there is separate optimization. The selecting the near user and far user itself is a research problem. So this is about the RSMA, and we will move on to the next topic, that is the massive MIMO. So basically, before entering into this massive MIMO, we want to know what could be this point-to-point MIMO is. So point-to-point MIMO, we will be having multiple antennas at the transmitter and the multiple antennas at the receiver. So practically, they have found this a long time back. That means in 1990s itself, this kind of experiments has been carried out, and they have observed that yes, it is theoretically it is effective, but practically there are a lot of difficulties in dealing with this, because one thing is our mobile phone, let's say our mobile phone, or even our laptops, they can't have multiple antennas inside. Okay, if our mobile phone is they claim that if our mobile phone is having multiple number of antennas, yeah, but I think for 5G they might be having, for 5G phones they might be having, but for 4G phones and all, if they are claiming that they are having multiple number of antennas, that is for uh, this LTE, and a separate antenna for Wi-Fi, or a separate antenna for a Bluetooth. Okay, so in that way they could say that they claim that they have multiple number of antennas with them. Okay, so the problem is in the MIMO, in the MIMO, point to point MIMO, the problem is there will be a matrix here. There will be a matrix, a channel matrix in between the transmitter and the receiver. Every time there is no assurance that every time this H, the matrix H, should be a full rank. Only if it is a full rank, then only it is very easy to, I mean, there will be a more theoretical gains, and there will be more gains there. Okay, so but in the cell edges there is a possibility that this matrix H will have lesser rank. Okay, that means there will be some sparsity will be there in the matrix, and so this point to point MIMO is literally a kind of failure. But this leads to something called multi-user MIMO. So what they do is they broken this one terminal having multiple antennas to virtually multiple number of users having single antenna, and they overall they consider that as a multiple antenna. So multiple antenna transmission and multiple antenna, the same kind of MIMO, but virtual MIMO. It's a kind of virtual MIMO, but this is multi-user MIMO because more number of users are involved in here. And yeah, you could see some kind of pre-coding has also been taken place at the transmitter. And the most important thing is M should be approximately equal to, what is M and what is K. M is M number of antennas are there. Okay. K is K number of users are there. So the number of antennas of the transmitter must be equal to the number of users, must be almost equal to the number of users. Then only multi-user MIMO is possible. Okay. Now, this is one thing to achieve a gain and overcome the difficulties of point-to-point MIMO. In the point-to-point MIMO, there is a possibility that the matrix H may fail. The matrix, the channel state information H may fail. But here we could see there is lesser probability that this link may get failed, and this will go to a null. Okay, so I mean the rank problem won't be there mostly. Okay, and we have some theoretical gains as well here, and it must be noted that CSI is required at the receiver and CSI is required at the transmitter. CSI means the channel state information, H. Okay, this channel state information is required at the transmitter as well as the receiver. Okay, now into the massive MIMO part. Okay, what is massive MIMO? When we have more number of antennas. Okay, when we have more number of antennas, then we say that as a massive MIMO. Let's say we have 200 number of antennas at the transmitter, and right now we have only some 8x8 configuration only mostly. Okay, in the transmitter side. So here the key thing is the user fellows, that is the user terminals, does not require any kind of channel state information. Okay, does not require any kind of channel state information for the processing. Okay. So instead, this base station, right, he is going to take up all the responsibility and do the encoding and decoding for them. Okay. So this is about the massive MIMO. So how it actually does that? How it is practically possible? Just a minute. See some mathematics behind that. The thing is, if the mobile terminal want to handle the CSI right now, our mobile actually handles the CSI, but every day we want to charge our phone, right? Let's say we have some low power, we are aiming for some less energy consumption. That means if I charge it for once, at least I have to use it for 1 week. My mobile phone, even after playing high resolution graphics video game, I should be able to use for another 1 week. So such a things are possible if we reduce the burden of signal processing things at the receiver to an extent. To an extent, at least in a prototype level, we should reduce the computational complexity. So how they are going to do this? So with the increase in the number of antennas, this is possible. So this massive memo is proposed by Thomas Marzetta. What he said is channel state information isn't everything, but it's the only thing. Okay, it's not everything, but it's the only thing. Okay, so how to justify this mathematically? Let's see a scenario here: MISO, multiple input and single output. Let's say I want to transmit an array of data from four different antennas. Then at the receiver, it will be a linear combination of the data and the channel state information, because between every antenna and every mobile, between every antenna and a mobile, there will be one link will be coming up. Okay, so it will be a linear combination of these things. Okay, but it is a bit difficult. I mean, the gains are not that good when this thing happens. Okay. So now they go for a matched filter kind of technique. So what is matched filter? So somewhere the receiver has to mimic the performance of the overall system. And that means a receiver or a transmitter should mimic the performance in between. That means I know what is the channel. I mean, the transmitter. Let's assume that the transmitter knows what is the channel it is going to deal with. Okay, so we have a mobile phone with us, and there are four links: H1, H2, H3, H4, and this CSI will be available with the transmitter, and based on that, it forms the beam forming weights. Okay, it obtains the beam forming weights, and that will be multiplied before data is been sent. It will be multiplied to that. Let's say S is the data that is going to be sent. Okay, that means this is the data we are going to multiply. That is, sorry, this is the beam forming vector we are going to multiply with the transmit data, and while traveling through the channel, it will be multiplied with the channel gain. Okay, H channel coefficient, it's not channel gain, channel coefficient. So what happens is at the receiver, when we are receiving this, we will be receiving it on a whole. So if you see H transpose and H star, that is H conjugate, they forms norm of H square. So norm of H square divided by norm of H, we could say that it is norm of H. Okay, because norm of H square divided by norm of H, we can cancel out the norm of H in the denominator and square in the top. So we have norm of H into S plus the noise. Okay, now what happens after this? What is this beam forming vector? Is, you could see W is the beam forming vector. It's nothing but whatever I have circled here, that is a beam forming vector, or we can say that is a matched filter vector. And you could see the SNR here is given like this. That is based on this particular equation. Based on this particular equation, whatever I am shading right now. So based on this particular equation, the SNR will be given like norm of H square sigma I square. Sigma I square is the signal. I mean the signal power, and norm of H square is the channel power, channel gain, and we have sigma n square, that is the noise. So this will be directly proportional to the number of antennas. Okay, this will be directly proportional to the number of antennas. Okay, now let's enter into the multi-user scenario, because this is the real scenario, right? We have one base station cannot be dedicated to one fellow. So let's get into this multi-user scenario. There we could see the all the user data. That is, let's say there are k number of users are there. Okay, k number of users are there, and this k number of user data is actually superimposed. Okay, superimposed after multiplying with the beamforming vector. Okay, after multiplying with the beamforming vector, and when it is received, it will be received like this. Okay, OA is equal to HI transpose, that is the corresponding channel state information will be multiplied with the superimposed signal X, and a noise will be added at last. So overall we will be getting an information like this. Okay, so what is this? How come this is possible? So when we substitute X in the place here in this equation, you could see HI transpose, when my I is equal to this I. Okay, let this be J. Okay, that is the better, I think that is right. This must be J. Okay, so when this I is equal to J, when this I is equal to this J, whatever J it is, the values are same, then whatever we have done in the previous slide, that is possible. So that's why we have the signal term here. Okay, this is the desired signal term, that is for the ith user. Ith signal is his data. Okay, so he have his own data. Ith signal will have his own data. Okay, what about the remaining data? What about the remaining data? This is interference. This is interference. Okay, so this has to be dealt, and this interference, as far as how much interference we are reducing, how much effectively we could go for effective communication, how we are going to reduce this, how it is going to be reduced is here. um, Here, if you see this, this is purely based on the number of antennas only. This H, the H is based on number of antennas only. If I am having n number of antennas, then we will be having n number of elements will be there in each and every channel coefficient. So when the channel when the number of antennas are very high, then there will be a lot of sparsity, and what happens is, as the number of antennas increases, this denominator, this interference part will be tend to zero, will be tending to zero. So what does that mean is, now my SINR is converted to, SINR will be converted to SNR. Okay, so um, so that's why we have this massive mimo in the place. Okay, so as far as the number of antennas getting increased, the SINR becomes SNR. That means the interference will be getting to zero. Okay. So how the number of antennas will also improve the directivity. Okay, so here you could see, if I am having one antenna, then signal will be going through all the directions, and the user will be getting a very less power. You could see the user here is getting around minus 40 dBm. Okay, this is minus 40 dBm. Okay, when we have one antenna, okay, m is equal to 1. Okay, what happens if you are going for 8 number of antennas? You could see the beam is actually focused towards a user. Okay, the beam is actually focused towards a user, but there are some side lobes as well. Okay, there are some leakage here as well. So this will create interference. If there is a user here, then whatever signal that we are sending to the desired user, that will be interfering this fellow. Okay, so this is when m equal to 8. What happens when m equal to 64? Okay, that means huge number. Okay, so 64 antennas together are serving the multi-user scenario. Then a particular user will be receiving his own data, and there won't be any side lobes. Side lobes percentage will be very less. So as the number of antennas keep on increasing, the performance is also getting better. Okay, but the amount of signal processing that has to be had by the base station is huge, but it can actually do that because it has the power. More power will be supplied to them. Okay, and we have massive MIMO beamforming. Okay, whatever we discussed so far is massive MIMO because we are going for more number of antennas, right? I didn't use the word massive MIMO, but instead more number of antennas. Okay, so massive MIMO beamforming. These are all some of the applications. Mainly, it can be used for this backhaul. That means for connecting the macro cell and micro cell, there will be for connecting the base station and the macro cell and the micro cell, there will be lot of wires, that means optical cables are also involved. Instead we can go for this kind of massive MIMO thing, and we can have a beam forming, beam forming and backhaul purpose can be served there. And also for taller buildings, definitely we can go for some virtual sectorization, and all the floors are equally treated, and they will get the appropriate network coverage. Okay. Now, what is this beamforming? So, beamforming, I'm assuming that to an extent the listeners are aware about this beamforming, and there are two types of beamforming. One is digital beamforming, another one is analog beamforming. So, in the digital beamforming, we go for the baseband baseband kind of beamforming, where multiple antennas are used, and this multiple antennas, each antenna will be connected to one RF chain. RF chain is a little costlier. Okay, it has a lot of nonlinear components, so RF chain generally we cannot use more. Okay, so why we are going for the discussion of beamforming is it actually contributes to it goes together with massive MIMO. Okay, so and we have RF chains, and each RF chain is connected to one antenna. And right now for massive MIMO we require 100 antennas, so we cannot have 100 RF chains there. So what we are going to do, let's look into the analog beamforming thing. So one RF chain is connected to, let's say, 10 number of antennas. Okay, so how they are connected? They are connected with the phase shifter. So this is analog beamforming. Okay, so this is the basic difference between analog and the digital beamforming. Now the real challenges, I can't keep the real motivation behind this hybrid beamforming is this millimeter wave does not encourages multipath reflection. Okay, so we have to go for this beamforming. No, we have no other choice. And this digital beamforming has a better performance with high cost. Why it is high cost means because it has more number, it requires more number of RF chains. Okay, it requires more number of RF chains, whereas this analog will be low cost because we are using only phase shifters to connect to the each and every antenna. So RF chain is one, but more number of antennas can be accommodated within that RF chain. Now we are going to combine this, but the problem with the analog beamforming is it has less flexibility. Okay, so so overall, we take the merit of digital beamforming and we take the merit of analog beamforming, and we are going to combine, and what we obtain is hybrid beamforming. So hybrid beamforming, what they do is they connect more number of antennas with less number of RF chains. Okay, so how they could able to do that? Because somewhere we have to connect RF chains with 100 number of antennas. Okay, so we have, let's say we have 100 antennas and we have 10 RF chains. Okay, this is a two types of architectures of hybrid beamforming. One is fully connected architecture, another one is sub-connected hybrid beamforming architecture. Here you could see each and every RF chain is actually connected to every antenna. Okay, so that's why it is called fully connected. Okay, you could see through phase shifters, it will be the RF chains will be connected to each and every antenna, and whereas here the first 10 antennas will be given to first RF chain, second 10 antennas will be given to second RF chain. So like that, sub-connected architecture, sub-connected hybrid beamforming architecture is also being followed. The complexity of fully connected is a little hectic, but still it is there, and